Twitch says we're live. Tonight's geology session is Nick Zentner's Supervolcanoes of the Pacific Northwest. This is part of his lecture series, which are quite engaging, actually, if you're into that sort of thing. If you're, for whatever reason, hyper-focused on a special interest, if you get my drift. He performs these at a middle school, like a community event. So these are free lecture series that members of the community within the city of Ellensburg, Washington, where Central Washington University is located, can attend a world-class geology lesson for free as like a community service. So he films them, he puts them up on YouTube. It's pretty dope. Anyway, so we're going to be watching that while we play some survival Minecraft. Off camera, I finished the roads in the local village where we left off in Jody's first world, and I found a better route back to the starter house and marked it out with torches. So now we have a path to make a road out to the village from the starter house. So that's what we'll be doing today in the Minecraft part. I should turn some of this down.
So the topic tonight is supervolcanoes in the Pacific Northwest. That's true. But I'd like to start with a story. And it's a story that involves Ellensburg, Washington, USA, right here. And many of you in this auditorium have vivid memories of a Sunday morning almost 40 years ago. 1980. Yeah, you're already reacting. You remember. But for those that were not here, let's go through the bullet points of what happened in Ellensburg, Washington on May 18th, 1980. It was a bluebird day. That's how the story begins. It was a beautiful morning, not a cloud in the sky. And there was no rain in the forecast. And those of you that were outdoors noticed the southwestern part of the sky, there was this gray cloud that started to appear. You're like, well, that's weird. I don't remember rain in the forecast. Is that like a thunderstorm coming from the Cascades? And then that gray cloud got bigger. And it got closer and bigger and closer and darker gray until by late morning, the entire sky here at Ellensburg, Washington was full of gray cloud. And it started to snow. At least it seemed like it was snow. What is this stuff coming out of the sky? I mean, it's dim now. I mean, we can barely see. The sun is blocked out because there's so much gray cloud. You remember this? And this isn't snow. This is volcanic ash. And for many folks, I think it took a while to connect what was happening on your forearm and that mountain they've been talking about in newspapers and radios for all that spring. That Mount St. Helens, a volcano in our state down by Portland, was going to erupt. Well, sure, the so-called experts said that, but by God, I think it actually happened because here's volcanic ash falling out of the sky and landing in Ellensburg, Washington, landing on the roof of this auditorium, and in the parking lot, and on the sidewalk, and on the windshield, and on the golf course, and in the hayfield, all over. And the rest of that Sunday, May 18th, was dark. The streetlights kicked on. And it wasn't just Ellensburg, it was many towns in eastern Washington.
Okay.
So the next day, Monday, the skies were starting to clear. And we had a souvenir of the eruption of Mount St. Helens. It was about a 1/4 inch of ash, a 1/4 inch of fine talcum powder. That was the consistency of the ash, kind of a silvery gray color. It's still around. That was almost 40 years ago. Now, if you go out and dig for that 1980 ash, you're bound to run into some other volcanic ashes as well out here in the desert. It looks a little different than this stuff that I brought in with me tonight. This is St. Helens ash collected from the roof of Lind Hall by Jack Powell, geologist. It's in a Weinerger's Wildcat Choco Mint ice cream container. So feel free to come up and enjoy. If you've never seen Mount St. Helens ash from 1980, we'll take a look. you and I together. We'll even open up and give you a little sample. So there are other ashes that fell out of the sky. So there are other layers that you can find out here in eastern Washington. Oh, well, here's an inch layer thick. That must be a different volcanic eruption. It is. That's Glacier Peak. That's Glacier Peak that sent some ash to the east. Here's Mount St. Helens that sent some ash to the east. Oh, well, and here's another ash bed that's from St. Helens, but it's more than 13,000 years ago. And that Glacier Peak eruption was more than 10,000 years ago. And it depends where you are with the circles. These circles are cone volcanoes with an erupting column. And the winds are blowing west to east. And they're taking ash from the eruptive column above the erupting cone volcano in the Cascades, sending it downwind, and sure enough, the ash is falling onto the ground. We are downwind of the Cascades. We receive the volcanic ash deposits from most of the Cascade volcanic eruptions. You can erupt Lassen or Shasta and get ash blown downwind.
That early game stuff, yo.
These super volcanoes? No, we're not there yet. Hang on, hang with me for a second. I'm setting you up. So by far the biggest of the ash beds from a Cascade eruption, many of you know. It's the Mazama ash that erupted 7,700 years ago. It was a Cascade volcano, a perfect cone that we call Mount Mazama. And that mountain almost totally blew itself up. The only thing left of Mount Mazama is just the stump, just the very base of that cone. Everything else is gone. And it has not rebuilt itself, by the way, in the last 7,700 years. So it's the Mazama ash that dominates, is the king of all of the ash fall deposits coming out of the Cascades. The Mazama ash, and here's Mount Mazama today. You know it better as Crater Lake National Park. That's Mazama. That's the beautiful blue lake is sitting in the stump of that Mazama mountain. So the end member, the extreme of what we think are possible Cascade volcanic eruptions is the Mazama event. And it's extreme. I mean, the Mazama ash here in our valley is a good 6 inches thick. I exaggerate. It's like a fish thing. I exaggerate. It's 6 inches thick. It is 2 or 3 feet thick, the Mazama ash that fell out of the sky over by Spokane, exposed right along I-90 on Sunset Hill on the north side. So you can get feet of volcanic ash falling out of the sky from Cascade volcano eruptions. But within an hour drive of here, south of Vantage, near the little town of Mattawa, there's 30 feet of volcanic ash. And it's 11.8 million years old. So it's far older than all these other ashes I've talked about. It clearly fell out of the sky, but there's 30 feet of this stuff. And it has been a puzzle for geologists throughout the 20th century. It was clear it was ash. It was clear it was ash that fell out of the sky. 30 feet. And in the geologic reports, with question marks, there was the message, there was some hell of an eruption in the Cascades someplace. But everybody shrugged their shoulders. I wonder where that was. End of story. Well, we now know the answer. And that's the reason for this lecture. That 30 feet of ash at Mattawa has been chemically analyzed now. We have ways to get a chemical fingerprint for an ash and connect it to its source, to connect it to its volcano. Like, who made this mess? Who made this 30 feet of ash? Who's responsible for this? The answer is a supervolcano. The answer is not the Cascades. The 30 feet of ash in central Washington, even though it's east of the Cascades, and even though there's a bunch of other ash beds that fell out of the sky from the Cascades, the Mattawa ash, the Saddle Mountains ash, came from a supervolcano in southern Idaho. There, I said it. I feel better. Let's draw that. Let's draw that. We're getting rid of the Cascades. The Cascades are done. They're dead to us right now. They're not going to help us at all. This is a supervolcanoes lecture. And to stall while I erase the board, let me tell you a pet peeve of mine. Have you seen a program on television or the internet about supervolcanoes? Where's the place that they all mention for supervolcanoes? Yellowstone Park, that's right. If they've got words on the program, fine. But they need video. They need to put video on the screen for their Yellowstone supervolcano story. What do they show? They show lavas from Hawaii. They show Mount St. Helens. They show the wrong volcanoes to correspond to the discussion of supervolcanoes. And I don't blame them, because humans have never seen a supervolcano erupt. Humans have never seen a supervolcano erupt. We don't know exactly what the experience is like. And if you're making a video program about a supervolcano, you can do your best, but we don't have any footage to use. And yet we have the 30 feet of ash in Mattawa. So let me put that X on again. What is that? That's the 30 feet of ash that fell out of the sky clearly. What's the date for it? 11.81 million years ago. Where's the source? Where's the volcano? It's not a cone. We're going to talk about different kind of volcanoes in a second. It's not a Mount Rainier cone. It's not a Mazama. It's none of those cone guys. It is a 30-mile wide crater, a caldera, called the Bruno Jarbidge Caldera. It's south of Boise. It's west of Twin Falls. It's near Jackpot, Nevada, if you know that place. I lived in southern Idaho for a while. I know about Jackpot, Nevada. The Bruno Jarbidge Caldera, a supervolcano, a caldera. And what I'm telling you is, 11.81 million years ago, stuff went down here. This thing blew, this thing exploded and sent ash through the sky 500 miles and landed here in central Washington. And I can't hold it because the energy is outstanding tonight. You are a great group. I'm going to keep rolling. Ash fell in Nebraska. Ash from the Bruno Jarbidge Caldera. That caldera right there made it to Nebraska as well as made it to us. And there's almost a dozen different eventual eruptions of that source. So we've got some work to do tonight, don't we? Was the wind blowing, north or something? Like, why is it coming up here? I thought all the ash is getting blown downwind to the east. What does this look like? Why isn't it a cone like all the rest of the volcanoes? What do supervolcanoes do when they do their thing? What is a supervolcano? Let's start with that. I did my master's thesis 30 years ago. I was a grad student in Pocatello, Idaho. I did mapping of ash flow tuffs we'll talk about in a second. There's not the word supervolcano in my thesis from 30 years ago. So even the word is new, supervolcanoes. So we got a lot of work to do, and I want to make it quick because I've got a healthy accumulation of video clips and photos and maps and everything else. Okay, crash course. You ready? Not all volcanoes on planet Earth are the same. It depends on how much silica you have in a magma chamber. These are underground rooms with molten material. If you have low amounts of silica, 45%, when that lava gets to the surface, it runs. It's very fluid. That's Hawaii. And the kind of rock that is created is basalt. We're loaded in basalt. We've had lectures on the flood basalts of eastern Washington, not the topic tonight. If you go to a coastal setting around the world, where you can actually mix oceanic crust with continental crust and increase the amount of silica present, the magma is going to be stiffer. It's going to build a different volcano. It's going to be a cone volcano. And you're like, are they really cone-shaped? You bet they are. Rainier, Adams, Glacier Peak, they're perfect, aren't they? Don't you still get a thrill if you've lived your whole life? Don't you still get a thrill when seeing that mountain on the horizon? That's an active volcano that's just perfectly formed and has erupted dozens of times, and we have ash beds to tell us that. So the Cascades are these cone volcanoes, but they are also not the topic tonight. Andesite is the kind of lava that's most common coming out of an erupting cone volcano, sometimes called a stratovolcano, sometimes called a composite cone. Remember, we erased the Cascades. They're there. We have done lectures on those. We're not doing it tonight. We are on this right panel. And I'm going to make this boundary. We've got students here taking notes for their extra credit, so get this, all right? We've got a major threshold of leaving the known to going to the unknown, meaning that humans have never seen these supervolcanoes do their thing. The most recent supervolcano explosion was 70,000 years ago in Indonesia, a volcano called Toba. Toba, a supervolcano. That's the most recent. So these shield volcanoes erupt constantly. Kilauea has been going since 1983 nonstop. These cone volcanoes erupt every few centuries. Rainier erupts every few hundred years. Will it erupt tomorrow afternoon or 5 years from now? Will a Rainier erupt 100 years from now or 200 years from now? We cannot forecast that with what we know now. But when we go to this last category, the topic for tonight, there are hundreds of thousands of years between explosions. So that's good news if you are one to, I don't know if I should drive to Fred Meyer tomorrow because of the supervolcano. I don't mean to belittle your anxiety, but these are very rare events. I'm on the pet peeve train. I might as well give you one more. Have you seen the articles? Have you seen Yellowstone's due? Yellowstone's overdue. Yellowstone. Why are you going to Yellowstone? Why are you taking your children to Yellowstone? It's overdue for a huge. That is total BS. There is no science behind that whatsoever. So please flush all those headlines. I don't know what they're doing, but it's got nothing to do with the science that we know in Yellowstone. Lord, I'm angry tonight. Why is that? You're here to enjoy learning some new material. Sorry for that. Sorry about that up in the balcony. Okay, so let's do this quickly, and then we'll go back and talk about the supervolcanoes that we have discovered. There's more than that one supervolcano. Ours, the one that made the Cougar Point tuff, the 11.81 million year old ash that fell in the sky here. So the quick and dirty version is this. If you have 75% silica magma, you are clearly in the middle of a continent. You have created magma that is so stiff it acts like toothpaste. It barely gets to the surface and just sits there and doesn't budge. And we build pressure as we trap gases underneath that cork of rhyolite lava. That's the kind of lava here. I'm not even going to write it out. I should. Rhyolite. So ironically, the most lethal of volcanoes are the tiniest little hills for hundreds of thousands of years. But then something happens. We finally get enough pressure built where we have something happen and we have a true supervolcano explosion. Let's do it real quick. We're going to do three things with a supervolcano explosion. Remember, we've never seen one happen, but we have reason to know what it looked like based on the evidence that's laying all over the ground. We've got our volcano. We've got our magma chamber with our 75% silica magma. We maybe have a little pimple of a hill, maybe as tall as Menashtash Ridge and no higher. Okay, finally it's time for a supervolcano explosion, whatever that means. And by the way, do we have any warning for this? Are there days, weeks, years? Are there centuries of build-up, warning signs before one of these goes? We struggle with the question because we've never seen one happen. But yet, when we finally do get the event, the first thing to happen is a major collapse of the roof of the magma chamber. We're sure of that. That there's a collapse of the crust as we evacuate a bunch of magma from underground. What we're forming topographically is a caldera. What I've drawn for you here is a circular feature that is the Bruno Jarbidge caldera. Each supervolcano is marked by a huge crater averaging 30 miles across, much wider than Crater Lake. Secondly, I can do it here better than that. We're going to fill the sky with ash. I don't care what direction the wind is going. We're not going to blow ash downwind from a supervolcano. A supervolcano is going to make its own weather. It's going to send ash in all directions, regardless of the jet stream or anything else happening. And the evidence for that is that we're finding ash from one particular supervolcano explosion across this entire map, all the way to Nebraska, but also out into the Pacific and as far north as central Washington. This is an equal opportunity offender. This is not just a few communities downwind. When I led a field trip to this site last November, everybody's talking about the wind. Oh my God, we got to totally change our view here, if we can, if it's possible. Well, this incredible ash, you can't even call it an ash cloud. I mean, it's everything within 500 to 1,000 miles in all direction of this supervolcano explosion. Eventually, the energy goes away, and all that material, all that ash and rock comes to rest. And it comes to the rest in form of a very descriptive term called a welded tuff. This is different than ash fall. This is ground-hugging clouds of ash flow that are traveling over the surface of the ground, as well as a bunch of other material that has momentum, finally losing energy, and is still white hot. So when it finally comes to rest, it's so hot that it welds itself. It's a great descriptive term for a change in geology. Welded tuff. It takes a hard effort. It takes hard work with a hammer, with a sledge even, to get welded tuff open. It was originally all this ash material, but it is dense rock. Sometimes welded tuff is called ash flow tuff. Sometimes welded tuff is called ignimbrite. Doesn't matter. We've got the concept, don't we? That surrounding this caldera, we're going to have about 100 miles of death, I guess, if you want to say it. That sounds like I'm on TV. It's a lethal area. I don't see anybody surviving within 100 miles radius of a supervolcano, because this is our area where we have welded tuff that most dramatically is flowing over. An ash flow is hugging the ground more than freeway speeds and killing everything. Plants, animals, anything else in its path. Finally, we're going to have some ash fall, some air fall, some material coming out of that huge sky dwarfing cloud, innocently falling on the surface. So my point is, we know the dates for these supervolcano explosions, not because of the hole in the ground. That's not going to help us. We're going to get dates from these welded tuffs. We can get accurate dates from the actual welded tuff material that surrounds the caldera. And then again, I don't have the time or the energy, but ironically, but we can have ash falling out of the sky over this entire map, all the way to Nebraska. Do you see how this is different than a cone? That we can't really talk about St. Helens or Rainier and these guys in the same breath? I hope so. Now I want to do one more thing on the chalkboard before we move on. And that is to plot our discoveries. Where have we found supervolcanoes in the Pacific Northwest? I don't know, maybe you had this discussion with somebody before you came. What's the title tonight of this talk we're going to? Supervolcanoes in the Pacific Northwest. What? Supervolcano, that's Yellowstone. He's calling Yellowstone in the Pacific Northwest. That's kind of a stretch. Yellowstone's in Wyoming. Yellowstone's in the Rockies. That's not the Pacific Northwest. I take your point. You're right. There is one of these 30-mile wide calderas in Yellowstone Park. That's why Yellowstone is such a freak show. Hot water is shooting out of the ground, old faithful geysers. Mud is boiling like pea soup. Stinks like rotten eggs. It's a volcano. There's a heat source beneath there. And the only other supervolcano we know about so far in this lecture is what I had for you just a few minutes ago. The Bruno Jarbidge caldera, 11.8 million. Well, let's get right to it. Where are the other supervolcanoes that have been discovered in the Pacific Northwest? Some of you know this. There's a bunch of them. Murmur. The crowd is murmuring right now. Let's move to Chicago. This does not look good. Well, I've got good news for you. First of all, I've drawn these calderas in an overlapping sense. And we don't know the exact size and location of each of these older calderas because they're now buried. If you get real pumped by this lecture and start driving south of Boise and looking for this big caldera, you're not going to find it because it's been buried by younger stuff and partially eroded as well. We have evidence at these spots, but we have to be kind of clever in how we find the evidence. But if you're totally confused why these calderas are lined up like this, and I'm feeling spunky, so I'm going to continue. This has been known for 50 years, that we have supervolcanoes number one, and that they're all lined up in this huge line. What's the relationship? Well, they're lined up. Aren't you glad you came tonight? But they get older as you go down the line. This youngest caldera is visible, is topographically a rim in the Yellowstone Park area. That caldera went 640,000 years ago. As we go down the line, the calderas get older. They're about 5 million years old by Pocatello, Idaho, where I met my wife and lived for 3 years. 10 million years ago, Twin Falls. 15 million years ago, south of Boise. 17 million years ago, northern Nevada. Let's keep going. 29 million years ago in northern California. And by the time we get above 50 million years ago, we have a heat source out in the Pacific Ocean. What in the world is going on? It looks like there's a heat source burning a hole in the continent, making a supervolcano explosion, and then it looks like the heat source is marching to the northeast. That's what it looks like. It's not what's happening. This is a geologic hotspot. Most of us view that hotspots are stationary. They do not move, but what is moving? North America. North America is moving to the southwest. North America is slowly drifting over a stationary hotspot. Can you do that in your mind? So the hotspot is not marching this way. North America is drifting over a stationary hotspot. The hotspot happens to be today here. But 11.81 million years ago, it was here. What am I saying? I'm saying that the ash at Mattawa is a Yellowstone story, not a Cascade story. Even our flood basalts, not the topic of tonight, is tied more to the Yellowstone story than it is the Cascades. So this is a major shift in how we view geology of the Pacific Northwest, just in the last 20 years. This chemical fingerprinting was done by Barbara Nash at the University of Utah, and she has run a microprobe lab for 50 years. And she gets people sending in ash beds from around the world, and she runs them through her instruments and gets a specific age and a specific chemical fingerprint and ties it to a particular volcano. That's how we know this ain't BS. Here's the last thing we're doing on the chalkboard. Uh-oh. Oh, good Lord. You heard of Smith Rock? It's a climbing place. It's a state park. It's near Redmond, Oregon. If you drive 97 from Ellensburg, cross the river at Biggs, Madras, Redmond, and then Bend, the Crooked River Caldera is right next door. Nobody knew about the Crooked River Caldera until 10 years ago. Everybody knew about Smith Rock. Everybody knew those were rhyolites. Everybody knew they were welded tuffs that were 29.5 million years old. Nobody had the imagination to map a caldera, which we now know as the Crooked River Caldera. So our last topic for the chalkboards is, why is this guy out here by himself or herself? What's the story? Well, it's not as isolated as it appears. Have you heard of something called the clockwise rotation of the Pacific Northwest crust? A topic we've talked about in this lecture series over and over and over again. The rotation of the clockwise crust of the Pacific Northwest. Northern California, Western Oregon, and Western Washington are rotating against Northern Washington and BC, which are not rotating. The results are the folds and faults of Central Washington. But what else can we do with a rotating crust? We can take a 29 million year old caldera in California and move it into Central Oregon. The Crooked River caldera, when it blew, was in Northern California. It's now in Central Oregon because of the rotation of the crust that's happened since that time. And in the works right now with the geologists we're going to meet by video are other discovered calderas, supervolcano calderas in Oregon that appear to be originally down here in this line and have been moved by this clockwise rotation. So if you're giving me guff about this title, supervolcanoes in the Pacific Northwest, they're in the Northwest. They maybe weren't originally, but they're here now. And they're creeping closer to you every day. Put that in your pipe and smoke it. Okay, take a moment if you would. Talk to your neighbor. Talk about how worried you are now about a supervolcano, and we'll get the projector going. Thank you. That's not a supervolcano, right? That's Mount Rainier. It's a composite cone volcano. It will erupt in the future. It's not our topic tonight. Not our topic tonight, but this is how we started the lecture with our story. And this is Mount St. Helens, what it looked like prior to 1980. And this is Mount St. Helens on the morning of its eruption, belching ash into the sky for the rest of that Sunday, May 18th, 1980. And the winds were blowing the ash from that eruption column eastward, heading towards the Morgan Auditorium. So here's our cone, here's our eruptive column. It is not a supervolcano scene. We are not sending ash in all directions. Here's Ellensburg, a few blocks from here. At high noon, too much ash in the sky to see the sun. And I realize if you're from Yakima or Moses Lake or Spokane, you had a different experience. It was darker, your ash was thicker. We get it. You're better than us. Screw you. All right. That was uncalled for. I'm sorry. So this is in the Yakima Canyon, and these are the ash beds we're talking about. This one that many of you know, we're still not totally sure which volcano produced it. This is 2/3 of the way down the Yakima Canyon. If you've heard Mazama, we have some chemistry and some ages that don't totally work with the Mazama story. So it's still up in the air. This one we do know, down by Benton City, near Tri-Cities, for sure it's St. Helens, for sure it's ash that fell out of the sky during the Ice Age flooding story, and the date is 16,300 calendar years before present. These cone volcanoes don't blow themselves up completely. They're still mountains. They still have elevation. They will rebuild themselves. But can we get a handle on volumes? That's one of the hopes for this early part of the slideshow. A rather meaningless number is to say that all the ash, quote unquote, and when I say ash tonight, I really mean with these volcanoes on this chart, all the lava and lahars and ash flows and ash fall, okay? I'll just say ash for short. So all that ash that came out of St. Helens in 1980 equals 1 cubic kilometer. So I can't picture that. Can you? Well, I tried. We can fill 1,766 rose bowls of ash, and that will be the amount for 1 cubic kilometer that came out of St. Helens. That's a lot of ash. I have to enunciate tonight. I got to make sure the H is there. Ash. That's a lot of ash. Vesuvius, Italy, that's 4 cubic kilometers, 4 times the stuff that came out of St. Helens. Krakatoa. You know, if you mention supervolcano, these are the names that people bring up right off the bat. Well, how about Krakatoa? How about Vesuvius? That was huge. Well, let's keep track of the numbers here. Vesuvius was in the 19th century, 18 times the volume of St. Helens. So that's more than 30,000 rose bowls from Krakatoa in Indonesia, a cone volcano. Crater Lake, Mount Mazama, up to 75 cubic kilometers, depending on who you listen to. but certainly dwarfing the amount of ash that came out of Mount St. Helens. Mount St. Helens was an impressive event. We all remember it, but we know that it's kid stuff compared to what we're talking about with these. Here's Mazama, southern Oregon, near Medford. Blow up most of the mountain. We're left with this huge hole in the ground. An impossibly blue lake called Crater Lake is a destination point for us today. And here's a map of the ash fall downwind of the Cascades, Mazama versus St. Helens in 1980. Okay, great. The Mazama here is right along I-90. Here's an exposure in Johnson Canyon, east of Kittitas, about 6 inches thick. Here's the Mazama ash along I-90. This is Andy Buddington from Spokane Community College. A couple of feet worth of ash. Mazama. We have a tectonic reason for the Cascade volcanoes. It's a subduction story. It's an ocean crust diving story. And as long as we subduct, we will continue to erupt volcanoes in the Cascades. Not the topic of tonight. Our topic is supervolcanoes. Nothing to do with subduction. Now we're going orange because we're crossing the threshold to supervolcano category. We're already up to 400 cubic kilometers, 400 times the ash that came out of St. Helens. The Valles Caldera in northern New Mexico. So I'm doing this for you, but you already know this from the chalkboard, hopefully. We are now over here to stay on the right panel with high silica, high viscosity lavas and caldera formations. Caldera, ash flow tuff, and airfall. Professional diagrams showing that. Here are professional diagrams trying their best to talk about the collapse during a supervolcanic event. And then something I didn't talk about on the chalkboards, there's commonly some resurgence of some of the lava. So we get these after the fact little domes that are common inside of these calderas. Resurgent domes we call them, made out of very stiff, toothpaste-like rhyolite lava. So let's get up in the air and look at some of these things. Here is the Valles Caldera, only 13 miles across. It's small compared to others, but look at how amazingly circular it is on a map as well. We're in northern New Mexico. And outside of the caldera, there's a state park, some of you have been to probably, northern New Mexico, Bandelier Park. And there's 1.2 million-year-old ash flow and ash fall tuffs that have an archaeological story where people were living in the supervolcano deposits related to the Valles Caldera. Now take a good can you memorize this photograph by the look? It's a very thick cliff. It's pinkish. It's kind of mottled in appearance. There's no obvious layering. That's what a welded tuff looks like. That's what one of these deposits looks like after the supervolcano calamity, and the ash comes together and welds to form this very dense rock. We're going to see this at a bunch of spots. You got it? That says supervolcano to many of us. Quickly, Long Valley Caldera, another supervolcano, this time in eastern California. If you're a skier, Mammoth Mountain is on the western margin of the Long Valley Caldera. It's north of Bishop. The Bishop Tuff is a very famous welded tuff. And of course, Yellowstone. Yellowstone, a plateau. It's a plateau for a reason. There's heat. It's heating up that portion of North America and creating a higher elevation than some of the surrounding areas. And in Yellowstone Park, have you ever noticed that the roads form a circle in Yellowstone? The road is following the rim of the Yellowstone caldera from the last supervolcanic event 640,000 years ago. Now here's what we did on the chalkboard, showing the march of older calderas across southern Idaho, which happens to be the Snake River Plain. And this particular figure, which is the conservative way to do this, stopped the trail of calderas in northern Nevada. I'm a fan of continuing them to the Pacific Ocean because of the clockwise rotation Oregon caldera story that is emerging in the literature in the last few years. Let's finish our list. Here's Toba, the most recent of the supervolcanic explosions. What are we up to now? How many Roseballs are we talking now? Good Lord, we got 3,000 cubic kilometers? These are estimates. These things are so big. And newly discovered calderas in the Rockies. The La Garita caldera, 27.8 million. We got 5,000 cubic kilometers. the Wawa Springs is the biggest known supervolcano caldera yet found in western Utah, 30 million years old, more than, so, I mean, at this point, they're just big numbers. We can't picture anything anymore. Oh, but maybe we can. Can't we take all the ash from that biggest known supervolcano and put it in the Grand Canyon? It would all fill one Grand Canyon. There you go. Bigger than the Rose Bowl. So one of our main objectives tonight is to not mix volcanoes, to keep those volcanic styles. It's apples and oranges and grapes, I don't know, something else. And so our Rainier is dinky compared to these systems that produce these supervolcanic events. And the ash plume, the physicists have been involved now to try to crunch the numbers and figure out how you get an umbrella cloud sending ash in all directions. We got to go to some places, don't we? Forget the diagrams now. Let's actually go to some real places and look at some real rocks and bring this a little bit closer to home. And as promised, here's the 30 feet of ash, south of Vantage. Specifically, where is this? Well, there's Vantage up at the top. You got your bearings now? We're looking north up towards Wenatchee. I-90 is going from left to right, or right to left, I guess. And here's the Columbia River coming through the Saddle Mountains. Up on top of the Saddle Mountains, looking north now, Vantage is off on the right, we can see it's a bunch of basalt lava stacked one on top of another. That's old news to us. We know that. But if you look carefully, there's a white layer. And you're like, oh, I just went to that lecture. I wonder if that's that ash he was talking about. In this case, it's not. That was cruel. Why did I do that? That particular white layer is called the Vantage sediment. And if you were with us last week talking about petrified logs on top of the Vantage sediment, that's the story there. That was a lake story and some hyper-concentrated flows of water going into the lake. So don't get carried away now, please. I appreciate your enthusiasm, but not every white layer out there is going to be this supervolcano thing. On the other hand, I think it's likely, now that we've learned about some of these new discoveries of supervolcanoes, that we will find more Yellowstone ashes in our area. In other words, we'll have people doing some analysis of some of the ashes that were assumed to be from the Cascades, but may be part of this supervolcano story. But we're on a mission to go to the 30 feet of ash north of Mattawa on the south flank of the Saddle Mountains. I don't know, does this look familiar? This is a State Route 243, I think it is. We're looking east. You're going from Vantage to Beverly, down to Desert Air, and then on down to Tri-Cities. That's it. It's on private land. I need to emphasize this. I'm going to get you all pumped up about this and show you pictures, but I got to say, you can't just go up there. I'm sorry. It took me a while to figure out how to get access to this place. But here's our 30 feet of ash on the south flank of the Saddle Mountains. These are drone shots from Bruce Bjornstad last fall. We're going to get in here and look very carefully. I'm telling you, this is the ash that came out of the sky from southern Idaho. And you're like, I don't think I believe you, man. Well, let me try to build a convincing case for you. And what's all with these markings? Why is it such a perfectly steep wall? Is there another part of the story here? In fact, there's kind of a natural patina to this Cougar Point tuff. It's called the Cougar Point tuff because there's truly a Cougar Point down at the Bruno Garbage area in southern Idaho where this stuff was first studied. And now we're tying it to this bed at Mattawa. But this is the natural look of the ash, and then it looks like snow. It looks perfectly white. Why is that? Do you have a guess? It was quarried. Our 30 feet of ash was used commercially in building the major dams on the Columbia River. Back in Roman times, those guys figured out that if you add ash to concrete, it enhances the concrete. Strength-wise, curing temperature, etc., even a finish to it. And so the next time you see Wanapum Dam or Priest Rapids Dam, think of the volcanic ash from southern Idaho that's in that concrete. And back when they were putting those dams together and quarrying the ash, this was an active scene, using local pozzolan to make the concrete for these big dams, the Columbia Irrigation Project, etc. Here's the old quarry road. As far as I can tell from the landowner, the last time they were quarrying up there was in the mid-1960s. And I'll give you evidence for that in just a second. So the first time I actually got up there, I'd known about this exposure for as long as I've been here, and I saw the scientific papers by Bardler Nash about 15 years ago, and I'm like, oh my God, that's a supervolcanic ash deposit? How do I get in there? So I couldn't figure out how to get in there legally, and I wanted to get up in there. And so a fellow who's here tonight, John Lasher, I want to publicly thank him. He had a friend of a friend of a friend who got me connected to the owner of the quarry. And last summer, went up there with a grad student and John and Carl Loquist. And I was more confused than anything else. I was excited to be up there. And there's graffiti from more than 100 years ago, by the way, scratched into the airfall tuff. But I was really confused. I knew it was a quarry, but there were a bunch of features. I couldn't even figure out how much was ash and how much was like river silt. And the confusion continued. And that's kind of how I operate anyway. I'm just kind of wandering around going, why is this so? You know, and everybody's tuning me out. But I couldn't wrap my mind around a lot of what we were seeing. And I was looking for specific evidence that this is a Yellowstone story and not a Cascade story. In other words, I was skeptical if this wasn't the Cascade volcano eruption story. Well, one of the reasons we know this ash is so old is it's part of a bed that is below one of our flood basalt layers. And in a way, the flood basalt layer above it, called the Elephant Mountain Flow, that's the one that has the beautiful columns, and I dropped my hammer by mistake down the columns at a different spot. That Elephant Mountain Flow has acted as a cap rock all these years. It has protected this softer ash. So if you saw those previous photos and like, why is that ash still there? It's just right there at the surface. Why didn't that erase long ago? And the answer is that overlying basalt protected it as a cap rock. Now this one really puzzled me. What are these things? There's just one portion of the 33 to 30 feet of ash that have these little BBs. And they're just about 2 feet up from the base of the 30 feet of ash. It's like, what? And we had a big discussion while we were out there, and Carl thought they were shells, and somebody else thought they were something else. And, you know, Facebook has got a lot of problems, but I do use Facebook after I go out and do some geology, and I get a lot of interesting comments and questions from people. And everybody wanted to talk about these things. Are those shells, or what are those seeds? What are those things? And I got some help from Jack Powell and a few other local geologists, and they said, look, you idiot. They didn't say it like that. Haven't you heard of accretionary lapilli before? I'm like, yeah, I guess, like 30 years ago, but I don't remember what it is. This is a common feature in thick deposits of volcanic ash. During the eruption, ash coming from Idaho, there was local weather, and rain got froze into hail, and the hail was coated in ash as it was going through the eruptive column. This is essentially fossilized hailstones with the rim of the ash still intact, 11.81 million years old. I said frickin', didn't I? And yet hollowed out because the hail has melted away. I'm like, that is unbelievable. And so I went back to my office and got on my top shelf a book I haven't looked at in 30 years, Pyroclastic Rocks, the Bible for volcanologists around the world, co-author Hans Schminke. I'm like, well, that name sounds familiar. And then I looked at page whatever it was, a black and white photo from this very famous textbook, Layers of Accretionary Lapilli, in pure vitric tuff, Ellensburg Formation, Sentinel Gap. I'm like, are you kidding me? This guy who wrote this book, who lives in Germany, who's a well-known volcanologist, was at this dinky quarry in Mattawa. So I found him by email. He's still alive. And I say, hey, Hans, did you ever spend any time in Central Washington? He's like, I have not been there. And this is my German accent now. I have not been to Central Washington in more than 60 years. But I was a young PhD student making studies, careful studies of the interbeds between the basalt lava flows. And I was at a place near Mattawa, where there was a quarry. And I'm like, are you kidding me? And so we went back and forth last fall by email, and he had all sorts of great stories. Here's one. So he's like a 22-year-old kid from Germany, and he says, I was up on the steep cliff of the north side of Saddle Mountains where I did some field work for a week or so, and I was brought up by some people because my car couldn't handle the silty roads. And then after 5 days, they forgot about me, so I started to walk back. And then they finally remembered to come get me, and my water supply was gone. So they actually got me, and they had some cold but bad beer named Rheingold. But in that situation, the best beer in the world. Hans Schmenke, we salute you. And these are the detailed photomicrographs of those lapilli with all these little broken glass bubbles, essentially. These little ash vesicles, basically, and down to the very tiny levels. These are in very tiny scale with scanning electron photomicroscopy. So it's definitely a volcanic story. Those lapilli are a big part of the story at this area. Now, here's more evidence that this is a unique deposit. This is some video of the Cougar Point Tuff. We're at the Mattawa Quarry. Look at how strong it is, number one. It's not ash that just falls through your finger, even though it's 11.8 million years. Number two, it was very sunny. I don't know if you can see this, but there's a lot of fresh, sparkly minerals in there. And number three, there's no black minerals in that ash. If you come up and look at the Weininger's jug of St. Helens ash, you'll see some black minerals. And I didn't know it at the time, but I know it now. If you are a Cascade ash, you have some black minerals in you. Some biotites or some hornblende minerals. That's just a thumbnail way to tell if your ash came from the Cascades or Yellowstone. Black minerals, Cascades, no black minerals, Yellowstone. Of course, there's other more sophisticated ways to make that case. This is also what Hans collected in the ash, these strange balls that we were confused by then, and I have to confess I'm still a bit confused by them. They're called concretions. They take forever to break open with a hammer. They're very, very hard. I just wanted to prove to you that I could get one open. And here's a little video with some of the accretionary lapilli kind of soldered onto these guys. The conventional message is these are secondary deposits. In other words, there's fluids, there's water percolating through the ash and forming these concretions. But that's not satisfying to me and maybe not to you either. Some of them are in god-awful shapes that you can find. I don't know what catalog this is from, but anyway. Hans had a request after about the fifth email. He said, I'm out of concretions. I use them in my teaching. And he must be 80 by now. I'm out of concretions. Can you collect a few and send them my way? So I made up a little care package of concretions and accretionary lapilli sent across the ocean to Hans. So that's the end of our ash at Mattawa, but not the end of the talk. There's other places you can find that particular ash from Yellowstone. Where can you go? Well, there's a place called the Pomona Lava Flow, named after the Pomona Tavern, north of Sela. And the Pomona Lava Flow is not present at Mattawa, at least in the quarry, but it did come in right on top of our ash. And when it does that, that heat of that Pomona Lava Flow baked the top of our Idaho tuff, our Cougar Point tuff. So you see it looks like we were just looking at it. This is on the north face of the Saddle Mountains, a drone photo by Bruce Bjornstad. And look at the top of our Cougar Point tuff is no longer white. It's orange and even kind of reddish brown. That's the heat of the Pomona flow baking that thing. I share this with you because if you know that drive on the freeway from Yakima to Ellensburg and Ellensburg to Yakima over and over and over again, you drive right by our Idaho ash every time. Does this look familiar to you? This is the baked upper part of our zone. Let me help you find this. We're heading south on the freeway. We're approaching the county line. You got it? We're heading south on the freeway to Yakima. We cross into Yakima County. It's the first outcrop on the left. This is the star of the show. There's a big reverse fault proving that earthquakes are a big part of our history. That's a story for another day. But off to the south, off to the right of this huge cut that was built back in the early 70s, late 60s, there's our baked Idaho tuff from southern Idaho, underneath the Pomona lava flow, and you can even see some of the pure Idaho tuff that we can see over in Mattawa much more clearly. Jack Powell's a local geologist, and he got these photos from me just in the last few days. I'm very appreciative of him. And you get into that orange-brown baked zone, it looks like glass. It is glass. It's almost an obsidian type of a look. So you can see that that overlying Pomona really did a number on our white ashfall tuff and welded it. And Jack found this in the top of that Cougar Point tuff that's been worked into an artifact by Native Americans. I can't hold it. I got to say one more thing. You know the big landslide south of Yakima, the one that's been creeping along down there at Union Gap? It's looking like the weak bed beneath that creeping landslide is the Cougar Point tuff, is our Idaho ash. So there's even an environmental part of this story. A couple quick photos from the big field trip we led last November, bringing you guys up there. Everybody was talking mostly about why is there 30 feet of this stuff? It's not 30 feet everywhere. Why is it so thick at Mattawa? If you look carefully at the details of the outcrop in the quarry, you can see evidence that there's plankton. There's actually diatoma. There's actually life, proving that there was water during at least part of the ash falling out of the sky. And these detailed photos prove that water was at least part of the story. Can you kind of see this rhythmic bedding going on within our ash? So to vaguely answer why it's so thick at Mattawa, it's been reworked. The ash has been remobilized and moved a little bit in the water, but I'm being purposely vague because I really don't understand why it's so thick there. Okay, I promise we're leaving Mattawa now. Goodbye, Mattawa, but I still want to go to a couple of places. Oh, wait a minute now. If it's a supervolcano and we're exploding ash in all directions, is it true that this state park in northeast Nebraska, damn near Iowa, has ash out of the sky from the same source? And why do they have a building over theirs, a shelter for their ash? We don't have that at Mattawa. Why are they protecting and actually having museum-type displays for their ash in Nebraska? Well, they got some goodies at the bottom of their ash.
One day about 12 million years ago, in the heart of North America, herds of rhinos were grazing on wide open grasslands, while turtles swam in the nearby watering hole. Early dogs hunted in the underbrush, and long-legged cranes searched the water for food. I like to think it started out as a nice day, but it definitely ended pretty terribly. The air quickly filled with volcanic ash, dimming the sky and falling to the ground in clumps, forming drifts like snowbanks. The ash coated everything, including the plants the animals ate, causing their teeth to become scratched and worn as if they'd been chewing mouthfuls of sand. And they unavoidably inhaled it, the sharp, glassy edges slicing at their lungs.
They have paleontology to do at the base of their ash from the same source as our ash. It's like, well, wait a minute. Shouldn't we go back out to Mattawa? Let's look for some rhinos. Let's go on a rhino hunt out there in central Washington. There's no evidence of megafauna that we know of at the base of our version of the ash. But this has been going on since the 1970s, the development of this state park and this painstaking work to find all these wonderful creatures that were living in eastern Nebraska almost 12 million years ago. Here's the founder.
My name is Mike Voorhees, and I'm the oldest living Ashfall volunteer. Ashfall is a state historical park, and the feature of Ashfall is prehistoric animal skeletons that are buried in volcanic ash. This was something that happened almost 12 million years ago. Herds of prehistoric rhinoceroses, camels, and horses met their death in a water hole, and their skeletons have been perfectly preserved now for 12 million years. And that's the whole point of Ashfall Park, is to give the public a first-hand view of a real paleontology site which is still actively being excavated.
It's just, is that pretty much just a straight ash fall type deposit?
Yeah,
then,
it's
at that point?
it's just, it almost reminds me of talcum powder. It's so fine. It's down, just a few microns.
Mm-hmm.
You know, a lot of volcanic ash is quite gritty when you
Yeah.
feel it, but this stuff is so far from the crater that only the finest particles made it this far. And if you trace this ash farther west, the grain size increases. There's a map on the wall that shows the
Oh, excellent.
source.
Yeah.
So it's a beautiful map they have at the park in Nebraska, but what's the problem? Where's Mattawa? So do you see? I love their map, but I see one problem with it. They're trying to include Mount St. Helens on the map, totally different kind of volcano, and they're giving the impression that the winds that day, 11.81 million years ago, sent the ash to Nebraska, which is true. The ash did travel to Nebraska, but it also went up to us. And so with this new discovery and this new set of scientific papers in the last 15 years, we can change these kinds of maps. So I did this at my desk with my colored pencils. So black line is our caldera, the Bruno Jarbidge caldera. What's the red? That's our 100 miles of welded tuff, our lethal zone. Nobody survives in that first 100 miles from the rim of the caldera. And then ash fall, on average, a foot of it in the brown and down to an inch later on. Now, we were just in eastern Nebraska. They had more than an inch, so there's these local reworkings of the ash again, which are a complication. And we have more than a foot of it at Mattawa. We've got 30 feet of it, right? So it's this local reworking that is a part of this that needs to be teased out. But let's go to the source. Let's actually go to the guy that made our ash, the supervolcano. And I'll do this quickly. 30 years ago, I was working on this. These are from my master's thesis. My study area was on the northern edge of the Snake River Plain. And I was working with supervolcano calderas that were younger than the topic tonight, but part of the Yellowstone story. Oh, here we go. Sure, why not? There's my fancy field equipment, a rock hammer, a clipboard, and a backpack with a bunch of Pop-Tarts in it, and that was about it. And I was working with welded tuff from the Heisey volcanic field, about 4 million year old, but the same general idea that you have these buried calderas sending these welded tuff, that's the yellow, and then those calderas are buried in younger basalt, so we really can't see the calderas today. Again, from my thesis, some of these nested calderas that are younger than 6.5 million, and I certainly was not talking about the Bruno Jarbidge. I definitely wasn't talking about Mattawa. I didn't even know where Ellensburg was at the time. Here's professional maps from Jennifer Hackett in Ellensburg. There's our supervolcano. There's Mattawa, that yellow dot. Here's ashfall fossil beds in eastern Nebraska, 1,000 miles away. So through time, what do? The calderas get younger and march their way across eastern Oregon, southern Idaho, that's us, Bruno Jarbidge, until the current location of the Yellowstone hotspot. Let's add the ash and the welded tuff. Makes you think, doesn't it? Where's all this ash? I know it's almost 12 million years ago, or 10 million years ago, or 5 million years ago, but did it all go away? We don't have the calderas anymore, I get that, but maybe there's a bunch more tephra deposits that can be tied to this marching caldera story. I did get some photos through Facebook from Rob Thomas, who teaches in Dillon, Montana. He said, we got a bunch of this ash up in Montana. Air fall, reworked locally. Now, to confirm this hotspot story, in case you're new to this, we have a trail of Hawaii volcanoes because there's a stationary hotspot in the middle of the Pacific Ocean, there's a moving ocean floor, and we get a line of volcanoes, one at a time. Only one is active at a time, and those volcanoes get older and older as you go away from the hotspot. in the direction that the tectonic plate is moving. Sound familiar? Of course it does. That's the same situation with the Yellowstone hotspot. Heat source beneath a thick continental crust instead of an ocean crust, making a totally different kind of volcano, a supervolcano now, instead of shield volcanoes made out of basalt. But in the gross scheme of things, it's the same trail of older and older volcanoes. I like this one. Kaboom! Supervolcano. Kaboom! We're drifting the North American plate over a stationary hotspot. I know it looks like that
Oh my
hotspot's
goodness,
moving.
buddy. Why
It's
did you
not.
wake up like that?
The plate, the continent,
I'm gonna
the
have
state
to
is moving to the southwest
Go.
over. You got it now?
'Cause
Great.
Dave's
So
awake.
the supervolcanoes look
Mom's
like
got
this.
it,
They
but
do not look
I
like
don't
Mount
know what his-
Rainier. They have the central
know what his beef
caldera and the
is.
welded tuff as a halo around the outside. Now, it's disappointing, perhaps, if you actually go to the Bruno Gerbich volcano, but maybe not if you like whitewater rafting. Friend Bruce Bjornstad took a rafting trip on both the Jarbidge River and the Bruno River and rafted right through the guts of our supervolcano. Here's our pink, massive cliffs, no layering, mottled look. I told you to memorize that before in New Mexico. Here we are again. How old is this stuff? It's 11.8 million years. The chemistry of these welded tuffs match perfectly with the ash just south of Vantage, Washington. That's the evidence that we have found the smoking gun, the supervolcano in southern Idaho, to connect this story. What an amazing place. You like this photograph, and I don't blame you. Welded tuff.
No, he's definitely up. So,
Deposited on the
Enjoy the
surface
end
of
of
the
the stream.
ground, very close and within the caldera at ground
sorry,
zero.
we can't finish the
Now I have to be
the talk.
careful. Each
but we're
of these
close.
major
He's wrapping
supervolcano
up.
calderas erupted many
Anyway, have a
times.
good night.
It wasn't just one kaboom.